Hello, dear friends, students. Today we'll be discussing about what they call as an molar specific heat of the polytropic process. Polytropic process may be represented as PV raised to n is equal to constant. This constant it changes depending upon the value of this particular index. Many of the oil cooled or maybe the water cooled engines, the practical heat engines, whatever they exist, they can be considered as an example of the polytropic process. We are discussing what they call as a molar specific heat of the polytropic process. Let's assume Cp and Cv to be as a specific heat at the constant pressure and the specific heat at the constant volume of the gas. Already we know that gamma, it's considered as a ratio of specific heat at the constant pressure to the specific heat at the constant volume. Let's say dq with the net heat supplied to a particular gas. We are properly considering the 1 mole situation. So I should say this has been given by C dt. So C represents the molar specific heat of the gas, which is in the polytropic process. Of course, from the pressure cooker example, the basic pressure cooker example, we can say that net heat, whatever has been supplied, dq, it has been used in two ways to perform the external work as well as to increase the internal energy. Du also it is the increase in the internal energy. It happens at the constant volume. And then let's say suppose if the heat is supplied to the system after the particular limit, the whistle is blown, the whistle moves upward, that is the external work done, which is PdV. So whatever the net heat supplied to the pressure cooker, it is used to increase the internal energy of the water as well as to perform the external work, this one and that one. So this is the increase in the internal energy happens at the constant volume, which can be given as Cv dt, and this is given as PdV, and the net is supplied, what it's given as C dt. Maybe I'll say it is the small temperature rise. Initially, let's say the temperature is Ti, and after finally the temperature reach is Tf. So whatever the small temperature rise, what is there within this entire process, I'll take it as dt. This entire temperature difference, I'll call that as a delta T. I mean to say T final minus T initial, I'll call as a delta T. T final minus T initial. Just remember these terminologies, whatever they have been used. So let's move on with the particular derivation. So all what we have is now C dt is equal to Cv dt, that is increase in the internal energy of the system, and PdV is the external work, whatever it happened. I'll cancel this. I've written this again. So the question still stays that if I have to find the net heat supplied, I'll have to integrate this. This gives me C delta T, CV delta T, and this particular integration, we have to apply some special rules. Not special rules, I mean to say rules of nth aggression. I'll say this is happening from V initial to V final. So let's deal with an nth aggression. I'll consider this particular integral separately. So Vi, Vf, and Pdv. That's how I'll start with. Now, from the initial assumption, Pv raised to n is equal to k, I replace this P with k upon V raised to n. So I do get V initial, V final, k, V raised to n dV. So with the basic laws of integration, I may get something as this, which is V initial, V final, K V raised to N dV minus. So that will gonna be V raised to, let's say N, V raised to minus N will be K, V raised to minus N plus 1 divided by 1 minus N. Means this minus N plus 1 only are written in a different way. So I do get 1 upon 1 minus N. K will get out of the integral. And I substitute the limits. So I will get V raised to 1 minus N. I put the limits V initial and V final, which of course gives me as 1 upon 1 minus N as V final 1 minus N minus V initial 1 minus N. That's how it looks. K, I'll keep it along with them. This I'll cancel it bit and I'll arrange K along with. Now, according to the basic assumption, I'll write P1 V1 raised to N is equal to PF PF raised to N. P1 means I'll say its initial, PF is its final. I'll call that as a constant. These constants, I'll replace them according to the convenience, whatever will feel as. So let's go for it. I'll just continue over here only. I have a very less photographic memory. Don't remember the things, whatever they're written on the previous page. So then this looks as 1 upon 1 minus the hell, 1 minus N, sorry. This K, now I'll write as PF V raised to F, PF V raised to F into V raised to F 1 minus N. This K, I'll write as PI VI into VI 1 minus N. By simple rules of indices, of course, what we get is something like this. I'm just cancelling everything over here. We'll just try to finish the integration on this page itself. I'll get 1 upon 1 minus N. This, I'll say it will become PF VF minus PI VI, which gives us 1 upon 1 minus N. PV is equal to RT. So if I apply, I'll get P1 V1 is equal to RT1, P2 V2 is equal to RT2, R2D2. No, forget it. So I'll get RT2 minus RT1 as how it looks. Let's continue with over here itself. And I get finally as 1 upon 1 minus N, R comes common. T2 minus T1, I'll get as again delta T. That is the net temperature difference between the final position of the, I'll say what, system and the initial position of the system. So finally I'll get R, R dt upon 1 minus N. That is our integral P dV from V1, V initial to V final. So if I replace that in the previous part, I'll get something as this. C dt or C delta T is equal to CV delta T plus R delta T upon 1 minus N. Delta T nicely gets cancelled. And we get something as, let's clear this first. We are just near to our result. It's not that great result at all. I never said that. But we get C is equal to CV upon R 1 minus N. That N is the index for that polytropic process. It's constant. This is N. And then suppose if I replace now CV with some other notations. We already know that Cp minus Cv is equal to R according to the Maer's relation. Cp upon Cv, we call it then gamma. That is the ratio of the two of the specific heats of the gas. If I replace Cp as gamma Cv minus Cv is equal to R, by simple algebra, I can take out Cv common. What do I get inside the bracket is gamma minus 1 is equal to R, and we'll get Cv is equal to R upon gamma minus 1. Cv, I'll get R upon gamma minus 1, where the gamma stands for the ratio of the specific heats. So this particular relation, whatever we already derived, I'll just replace Cv with R upon gamma minus 1, and I'll get molar specific heat of the gas in the polytropic process as R upon gamma minus 1 plus R upon 1 minus n. That was like that. This is the final answer, what is expected. LCMs and all, you can take it, you can simplify this particular expression. You can show your skills if in case if you want. That's the further story. But let's stay down over here. Polytropic process means I should say that when the process starts at V initial and it will go up to V final, it can come down by many different paths, maybe whatever I understood as. Still, any other information anybody has, specifically the industrial application of the particular system, you are all most welcome. Comment them, let's say, in a particular section. Thank you very much.